This is lesson 7, combining linear and geometric models of growth and decay. The learning goal is to look into the format of how a geometric and linear recurrence relation works, and to see this recurrence relation in real-life context. The success criteria is to be able to create a linear and geometric model given a monetary example, to use this recurrence relation to find specific end terms, and to find yearly, monthly, quarterly, or fortnightly percentage rates given a recurrence relation. So far we've looked at linear and geometric models separately. Now we'll be combining them together, and when we combine them, they can be used for either reducing balance loans, so paying off a loan of some sort, and also investments where you're actually adding money into the investment on top of the bank giving you interest as well. So let's have a look at this example. When graph geometric and linear growth, the recurrence relation is as follows. We have an initial amount, v of 0 is equal to some amount a. And to get the next term, v of n plus 1, we get the previous term, multiply it by a common ratio r. And then we have this new thing that tags along where we're adding a common difference. And there's a few protocols that we have to follow here. The common ratio r will always be greater than 1, and that's normal for geometric growth. And then this thing that tags along here, it has to be a positive number that's added. It doesn't matter whether it's between 0 and 1 or greater than 1, that makes no difference, no pun intended, as long as it's added at the end. So an example here, we have an initial amount of $2,000. To get the next term, we get a previous term, multiply by 1.05 or 5% of what the previous term is, and then add 100. Now, a real life application of this is investments with payments. I have an account that mimics a recurrence relation for geometric and linear growth. I have an initial amount that I put in there. I have a percentage that's compounded monthly, but then I'm also adding money into the account per month. Now obviously this varies how much I put into there, it depends on how much I spend within that month and what I have left over. But the rule that the bank has is in order for them to pay me interest, I have to have a minimum amount of $50 per month in there. So I'm just gonna, at minimum, put in $50. So think of it in that way. In this case, there's a minimum of $100 that is being put in. Now obviously you can add more if you want, but for the sake of this example, that's what that plus 100 is. This curves up from left to right. For geometric growth and linear decay, the recurrence relation is exactly the same. There's only this minus d that's tagging along. But usually, we're so used to geometric decay having a common ratio value r being a number between 0 and 1. When you're combining geometric growth with the linear component to it, your coefficient or the common ratio again will be greater than 1. Just this thing that's tagging along is a positive number. D is a positive number, but it's subtracted. Okay, again, it can be between 0 to 1 or greater than 1. As long as it's subtracted, we have a decay. And remember, this has to be greater than 1, the common ratio. So another example, $15,000 is my initial amount. In order to get my next amount, we get a previous amount, multiply by 1.03 or 3% of the previous term, and then subtract 2,000. Real life application for this is reducing balance loan or even a mortgage. I'll be paying a mortgage off soon once my house is complete. And with that in mind, I will be chipping away at it. And say for instance, I pay $2,000 per month. Now, as I'm chipping away at it, I'm still having 3% of that multiplied to what the previous amount is. So obviously, the more I pay off, the more interest I will have to pay on top of this. But as a base, I have to make sure that 2,000 is being taken away each month. When graphed, this will look like a curve that goes from left to right. The difference is it doesn't seep straight down to the x-axis like we're used to for geometric decay, but rather a bump from left to right. So with this formula here, we can see that this is the template for it. Capital R is your common ratio, and this can be found if we know what our rate is and we know the amount of payments that is made within the year. If the common ratio has just been given to you, we don't have to use this. And we've got to remember that small r's are interest per annum. The P is the number of times compounded per year. This could change depending on whether it's quarterly, fortnightly, monthly, or daily. And capital D is the regular payment to the investment. And this is just for regular payments. So let's have a look at this example here. Megan invests $500 into an account, earning 8% per annum compounded annually. She deposits an extra $500 into the account each year after the initial deposit. We're going to write a recurrence relation to model this situation. So how would we attack this? First, we got to figure out what the common ratio needs to be. Because remember, the common ratio is not just 8, this is a percentage. What we do know is the formula for this. So it's R plus. Now, how many times is this compounding per year? It's just 1. So it's just going to be 8, which is the 8% over 100. And this equates to 1.08. So our common ratio is 1.08, but then also we've got to take into consideration that Megan is paying an extra $500 as well on top of this. So our D value, or common difference, is 500, and it's positive because it's added onto it. So to write our recurrence relation, we always start with V of 0. I'll just scroll this down, see if I can get enough room. So a V of 0, our initial amount, how much is she putting into the account as an investment initially is 500. To get our next term, Vm plus 1, we get a previous term and we multiply it by 1.08 and then add $500 on top of this. And this right here will be a recurrence relation for this example. And we're going to use this recurrence relation to answer B. How much does Megan have in an account after 10 years? Or in other words, we're going to try to find out what V of n is. So to get V of n, we need V of 9. To get V of 9, we need to get V of 8. V of 8, we get V of 7, etc. Now, fortunately, there is no rule for the nth term when you're combining linear and geometric. This isn't possible. So the thing we have to do is grab our trusty calculator and try to figure out the amount after the 10th year. In order to do this, get your calculator out, press the sequence function or the sequence app, and in here we're just going to copy down the recurrence relation which combines the two. So it's 1.08 multiplied by V of n, in this case A of n, plus 500. Execute this and make sure you set your initial amount as 500 as well, because we can initially invest 500 into the account. Next thing, we want to set our limitations. Now, we are trying to look for after 10 years, so V of 10. So our n number will be 10, okay? We're not looking for the 10th term, we're looking for after the 10th year. Press OK, you get your table up, resize this, and then we can see after the first, second, third, all the way to the 10th year, we end up with $8,322, and specifically for this amount, 74 cents. So our V of 10 rather, is $8,322.74. The next example, Kim opens a savings account with an initial investment of $3,000 at 6.5% per annum compounded quarterly. At the end of each quarter, she makes a deposit of $2,000. We're going to write a recurrence relation to model this situation, and then we're going to use this recurrence relation to find how much Kim has in her account after 3 years. So we're going to be careful with that part B to it, because it's 3 years and there's a quarterly compound. We'll get to that in a second. First, we need to figure out what our common ratio is to write a recurrence relation. So in this case, this is going to be 1 plus whatever our percentage rate is, it's 6.5. Now this is where that little p comes into, because we've got to put the 6.5 over however many compounds happen within the year. Because this is compounded quarterly and there are 4 quarters within a year, this is going to be 6.5 over 4 all over 100. Okay, so remember that formula here, 1 plus r over p all over 100. When we get this amount, we put this into a calculator, we end up with a decimal 1.01625. Now with this common ratio, we can write our recurrence relation. So always start off with V of 0. She initially deposits $3,000. And to get the next term, V of n plus 1, this is equal to V of n times whatever the common ratio is, 1.01625. And then we're also going to add a common difference. At the end of each quarter, she also makes a deposit of $2,000. So there's a plus $2,000 tagging along. We're then going to use this to find out, that should be B rather, there we go. We're then going to use this to find out how much Kim will have an account after 3 years. Just move this to the side here, here we go. Alright, so we're finding V of 12. Now, why are we trying to find V of 12 and not V of 3? Because it says 3 years. And this is because this recurrence relation is bound on quarterly compounds. So after 1 quarter or 3 months, you'll get a certain amount based on this being the initial and what is being added onto it. That makes sense. So the amount of compounds there are within 3 years is 12, as 3 times 4 is 12. And we're going to put this into the calculator. So there's our old one. Let's get this resized again. Let's clear this. So let's put in 1.01625 multiplied by A of n, and then we're going to add 2,000 to this, and our initial deposit is $3,000. We're going to set this as start 0, end 12, because we're trying to look for after the 12th compound, which is the 3rd year. Get the table up, resize this, and at the end of the 12th year, we have $29,906.77. So you got to remember that even though we initially started off with 3,000, we're getting a certain percentage rate on this with a common ratio, but we're also adding 2,000 every single time. So of course it's going to keep growing at quite a good rate, because when we get that quarter of 6.5%, it's going to happen on the previous amount, which is going to actually increase quite exponentially. So very, very good investment. Well done, Kim. So V12 is equal to $29,905.77. Now let's be realistic with this. $3,000 is not hard to save. Full-time, part-time. $2,000 with a full-time job, if you were to put this in every 3 months, is actually doable. And 6.5% compounded quarterly. Generally it's compounded daily and paid monthly. That's how banks commonly do this. But this amount right here, after 3 years, can realistically happen if you're putting $2,000 every 3 months. That's quite a bit of money. That's almost like a car loan. So if you're willing to save, and you're willing to save hard and do this for 3 years, the bank can be your best friend within this scenario, because they're willing to pay you interest for using their service. All right, now we're going to look into reducing balance loans, and this one can be a bit tricky. Same concept, the only difference is we have a subtraction. So we're going to be taking away a certain amount. And this has to do with loans, okay? So if you see the word loan and not investment, loan, you know we have to do a subtraction of some sort. So Carlos borrows $40,000. There we go, borrows as a loan. $40,000 to landscape his garden. The bank lends him this amount with interest calculated monthly at a rate of 9.6% per annum. To repay this loan, Carlos is required to make repayments of $873.69 each month for 5 years. We're going to write a recurrence relation to model the situation, and we're going to see how much Carlos still owes after 3 years. All right, how are we going to do this one? Firstly, we need to make sure that we know what our common ratio is. So a common ratio, again using this formula, this will be 1 plus. Now what is our rate? The rate the bank is saying is 9.6. So it's 9.6 over. Now what is the amount of compounds that is happening per year? Or in other words, how much is Carlos paying? What's the compound amount that Carlos is paying? Is he paying per month, per year, per week, per day? He is making repayments each month. And how many months there are in a year? Is 12. So a P amount in this case is 12. If it said he's paying it this amount every fortnight, that would be 26, because it's 26 fortnights. Yeah, that sounds right. Yes. All right. This is all over 100. When you calculate this, your R value is going to be 1.008. So now our recurrence relation, I always write V of 0 is equal to what the initial amount is, 40,000. And our V of n plus 1 is equal to the V of n multiplied by 1.008. Now remember, this is a loan, so we're going to be taking away a certain amount, a common difference. And we know what is being taken away because this is the agreement that the bank made for Carlos to pay off. $873.69. So this right here will model what the next terms will be using the previous term. Now, I just forgot V of n, there we go. And there's our recurrence relation, and we're going to use this to predict how much Carlos still owes after 3 years. So after 3 years, we need to find not V of 3, but in fact V of 36. Because Carlos is paying this monthly, and if there are 12 months within a year, and we're just trying to see what it's going to happen after the 3rd year, 12 times 3 is 36. We're going to put this into a calculator and see what we get. Alright, I've gone ahead and put this into the calculator, making sure that this was a subtraction of the correct amount, and our starting amount of $40,000. I wanted to get the end result of 36 because we're looking after the 36th month, which is the 3rd year. And when we get the table of numbers here, we can see that this is going down, down, and down. So he's chipping away at it. He's paying $873.69. So once he pays that, 1.008 common ratio, or 9.6% is then calculated on that. And then that's how much he owes. And then again, he pays off $873.69. And this keeps going. So after the 36th month, which is the 3rd year, our amount is $17,006.96, because that 7 bumps that 5 up by 1. All right, last example here. The following recurrence relation reflects a housing loan. Interest is compounded monthly. The starting amount, $450,000. And to get the next amount, you multiply the previous amount by 1.005, and then you subtract $3,797. Now, let's have a look. How much was that loan for? How much was that loan for? So the loan, how much it was borrowed, is just the initial amount here. So the loan This is just equal to 450,000. How much are the repayments? Well, the repayments is that common difference that tags along at the end. So the repayments, this is just equal to $3,797. For C, how often are the repayments made? Well, the following recurrence relation in the house loan interest is compounded monthly. So how often are the repayments made? Well, they're paid monthly because it's monthly repayments. The easy stuff. Sorry, there's flowers. It's got all these little animations that tell you what each tool does. And hands tool. Cool, that's great. I get distracted. Okay, D. What is the monthly interest rate? All right, so the monthly interest rate, we need to figure out a few things. Because this recurrence relation is happening monthly, and we need to find the monthly rate, all we need to do is find the difference between 1.005 and 1, and then just multiply this by 100 because of that common ratio here. In this case, the monthly interest rate is at 5%. But then this becomes different. This becomes different because now the next question says, what is the yearly interest rate? Sorry, this is not 5%, this is 0.5%. 0.5. Yeah, that seems better, not 5%, 0.5. This becomes different now because we figured out what the monthly rate is. The monthly rate isn't the rate that's provided by the bank. They always give you what the yearly interest rate dictated by those letters PA, per annum. So to get the yearly interest rate, there are two different ways that we can go about this. We can either get our monthly interest rate, 0.5, and just multiply this by 12. And this will give us a yearly interest rate, which is 6%. The other way you can do this is using the solve function, and then you can solve for this 1.005, as that's our common ratio, is equal to R, which is the rate we're trying to find out, divided by 12, because there'll be 12 compounds within the year, over 100, and we're solving for R. Or you can use X within the calculator. Again, when you put this in, this will also spit out 6. So the yearly interest rate is 6% per annum. That concludes this video. A bit of a long one, but there was quite a lot of information specifically for this exercise. We are getting towards the end of this. This is lesson 7. This is all you will need to know in regards to the upcoming SAC. The next lesson, lesson 8, is to do with the financial solver, which will be provided to you by a project. More information will be coming about that within the given time. For now, check your log sheet, see what you need to do, and I'll see you in the next video. Bye-bye.